I am excited to introduce our paper titled Vision-Aware Text Features in Referring Image Segmentation, from Object Understanding to Context Understanding, which has been accepted at Wacv 2025. This is a collaborative research from the Hong Kong University of Science and Technology, Stony Brook University, Trinity College Dublin, and Ho Chi Minh University of Science. Referring image segmentation, or RIS, is a process that segments objects within images or videos based on textual descriptions. This task has practical applications in batch image editing, where users can manipulate specific objects through text commands, and in human-robot interaction, allowing robots to understand and execute tasks based on textual cues. However, RIS faces challenges such as handling a large vocabulary to accommodate diverse descriptions and establishing a robust alignment between textual descriptions and visual elements. In RIS, the complexity of the task increases with the complexity of the descriptions. Simple descriptions like left girl are easier to segment compared to complex ones like a shiny red vintage pickup truck or a brown horse wearing a mask ridden by a jockey in dark red. As descriptions become more detailed, accurately segmenting the referenced objects becomes significantly more challenging. Current state-of-the-art models often encounter difficulties with these complex descriptions. This is because existing methods have relied mostly on visual features to generate segmentation mask, while treating text features as supporting component in the Fusion module only. This underutilization of text features limits the model's capability in challenging expression, especially in the case the expression contains unseen object vocabulary or contextual relationship between object. Let's look at an example using the LAVT model, a state-of-the-art approach in this field. When given the expression, an orange striped fish on the left, LAVT correctly identifies the object. However, regarding a more complex expression, a clownfish facing towards the camera, LAVT incorrectly segments the wrong object and oversegments the image. This inconsistency highlights the model's difficulty in handling specific vocabulary, clownfish, and understanding spatial relationships, facing towards the camera. These examples illustrate how the underutilization of text features can lead to inconsistent and incorrect segmentations, especially when dealing with complex expressions. Our method is inspired by how human can solve RIS. Given this image and text, we need to segment the front bull in this case. When given a complex expression, humans don't process the entire sentence at once. We first focus on two questions. What is the subject, or the main object of interest? What is the information in the sentence or the description corresponded to that subject? For example, this expression can be decomposed into the bull as the object of interest and seated on the ground facing the camera as a context information. In the next step, we will find the potential candidates that match some characteristics of the object of interest, name or categories. It will help to reduce the search space a lot. Instead of looking for the whole image, we then just need to look on specific region. We then use the context information or description to pinpoint the target object from the list of potential candidates. Inspired by human approach to RIS, we first identify the main object of interest, the bull, which we call object understanding. Then, we use the rest of the expression to pinpoint the exact instance, which we term context understanding. This decomposition allows a more comprehensive utilization of both visual and textual information. Our contribution is as followed. First, we propose Vatex for a better text understanding. We decompose it into object understanding and context understanding. We propose a clip prior module to embed clip visual heat map in query feature, effectively handle hard vocabulary scenarios. We propose Contextual Multimodal Decoder, CMD, followed by a Meaning Consistency Constraint, MCC, as in-context learning signal to improve context understanding. We first move to our first contribution, Object Understanding with Clip Prior. Clip Prior receive the image and expression as input and output the clip-aware query feature. Here is the detailed pipeline for our Clip Prior module. The input text description will be decomposed into the main noun phrase and context information using main object extractor module, which is a dependency tree-based approach. We then convert the main noun phrase into a template-based sentence. A photo of object. After that, both image and the template sentence are then feed to clip, result in image embedding and text embedding. The visual heat map can be obtained by calculating the dot product between the normalized visual and text features. To embed heat map prior from clip into the query feature, as a normal practice, we first change its dimension to C. Then repeat it n times together with the text features to create n object queries, each with dimension of C. This clip-aware query feature will contain both visual and text information. Our second contribution lies in how we can understand the context from both image and text input. After obtaining the text and visual feature from the backbone, these features are passed through contextual multimodal decoder to enable multimodal interactions, yielding vision-aware text features and text-guided vision features. Contextual multimodal decoder, CMD, is proposed to produce multi-scale visual feature maps while enhancing contextual information from the image into text features. The bidirectional attention transfer, BAT, module is simply two cross-attention layer to fuse multimodal information. In the language-to-vision branch, these multi-scale feature map contains text information about target object, and this is one of the two main components to generate the segmentation mask. It will contribute to the segmentation loss as a direct learning signal. The final text features contain visual information about the object and its relationship. Previous methods do not utilize these features, results in the inconsistent mask prediction. On the other hand, we propose to add a constraint on these features as an in-context learning signal to create a robust, profound, coherent text feature space. Our contrastive learning ensures semantic consistency across varied textual descriptions that reference the same object. Given image and a target object, there are different ways to describe that objects. Consider this example. There are two horses in the image, and we can describe it by three different ways. Denote P1 and P2 are referred to the red horse as representative for +1 and +2. The green horse, as a negative example, denote as n. We then calculate the cosine similarity between these embedding vector. As we can see that there are not too much different, around 0.5 to 0.6. MCC aims to learn meaningful and discriminative representations for different expressions, while pulling sentences referring to the same object close to each other. During training, we construct a triplet of expressions for each image. Each triplet comprises two sentences that refer to the same object, positive samples, along with a third sentence describing a different object, negative sample. We adopt the info NCE as our contrastive loss. This pairwise similarity matrix before and after significantly changes, especially the cosine similarity between positive samples increase and between positive and negative sample decrease by adding extra conditioning on the image. Here are some experimental results with Vatex. We evaluate the performance of our model on three standard image datasets: RefCoco, RefCoco Plus, and gref. Our method outperforms the state-of-the-art methods by a large margin in all splits of different datasets. Notably, our method surpasses the recent VG law, ranging from around 2.2% to 5.5%. Compared to LISA, a large pre-trained vision and text encoder, Vatex also consistently outperforms it by 3 to 5% across all datasets. Furthermore, Vatex also demonstrates the superior performance over LAVT, RELA, and CG, former on average precision metrics, particularly at the precision at 0.7 and precision at 0.9, illustrating our ability to generate high-quality and complete segmentation masks. Our model can be extended to video datasets with minor adaptations to handle temporal information. Vatex outperforms the state-of-the-art methods VLT and RefReformer on the same backbone by 1.6 and 3.8 J and F on the Ref YouTube Bashvos and Ref Davis 17 datasets, respectively. Our research presents qualitative results on the RefCoco, RefCoco Plus, and gref datasets, illustrating significant advancements over existing methods. The LAVT model frequently identifies incorrect objects and produces incomplete masks. In contrast, our method demonstrates superior performance, particularly in complex scenarios. It excels at distinguishing between similar objects and accurately localizing specific instances within a scene, thereby enhancing the precision and reliability of segmentation in challenging contexts. We conduct an ablation study. Every component contribute to the better result. The combination of all modules lead to the best performance, up to 7.7% in MIOU and 5.6% in J and F. Thank you for your attention. For further details, please explore our webpage and refer to our paper for more in-depth information.